So far, we studied about how to model interactions. There is a typo here. Interactions in a system. And we completely forgot about electrons. We like, yeah, electrons are there. We don't care about it. We only care about rigid spheres or like, coarse grained models. But electrons are there and they're here to stay. They're not going anywhere. All the reactivity that comes out. If you want to understand chemical reactivity, you need to understand how electronic and nuclear rearrangements occur. Because essentially, what is a chemical reaction? If you think about it, you start with the reactant, you end up with the product. Nothing gets lost in between. I mean, there might be a gas escape, but that's part of your product. So it's essentially rearrangement of the atoms and the atoms that constitute a molecular fragment on the potential energy surface. So you can say, okay, this is stable on this side. It went over the hill on the other side. So you start with the carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, whatever. You combine them in a certain way, and you get a drug that cures some very vicious disease. Or you create a material that can revolutionize your oil and gas sector. So understanding, including electrons, is very, very important. We cannot ignore them. I mean, we can make a lot of predictions with force fields, but if we want to understand chemical reactivity, we need to consider the reactivity of electrons. Let's make a simple visualization here. So what you see in the picture are the large ones, these large black spheres. They are essentially nucleus. Makes sense, nucleus are bigger. Even in a hydrogen, a proton is 1800 times heavier than an electron. So bigger. I don't remember the radius exactly, but one can agree that it's bigger. And then you have electrons. Let's say you can imagine that maybe this is a hydrogen molecule, H2, one proton, one electron, one proton, one electron. And we try to see at a given nuclear distance, internuclear distance is RA prime. Maybe I will go to the presentation mode. Where did it go? Yep. Oh, this option disappeared. How do I do function F5 or something? Oh no, that was not a smart idea. Okay, let me get back to my more interesting slide. Okay, and here I can choose my laser pointer. So this is a nucleus, this is a nucleus. Nucleus is positively charged, right? It has protons and neutrons. We forget about neutrons in computational chemistry. We say there is some separation, which means it will repel each other. Now, if you think in very simple terms, it's amazing that atoms could make bonds, right? If you look at an atom, you have a proton and an electron that attract each other. Another atom, same thing. And if they come together, electrons will repel each other, nuclei will repel each other. Yet, the charge density flows in such a manner that you can actually, this electron can also get attracted here, this electron gets attracted here, and bonding occurs. So the distances that are there, they are very important. The interaction is very important, and we can no longer think of them as being connected by a spring. You could, but then you would lose the actual quantum mechanical picture. So now that you have this figure etched in your memory, I hope you do, but I'll keep repeating it. Let me drop a big mathematical statement or a mathematical expression, which I don't want you to be scared about. Take some time with your diagram, with this diagram. Forget about this for now. Do you understand this diagram? Is there something that that is unclear to you, what this represents? Okay, seems like it's clear. People understand what this is. Now, let's see from this diagram, how do we derive the interaction energies in the system? And I really don't want to think of it as a big mathematical thing with summations and whatever. And by the way, there is a small mistake here in the Hamiltonian, which I challenge you to spot. It's a stupid mistake, but anyway. So the The Hamiltonian is essentially the kinetic energy and the potential energy. Now we are not talking about kinetic energy in terms of half mv square, like there is a velocity or something. We are not talking about that because we treat electrons as waves. And if you have some background in wave mechanics, so classical wave mechanics, the derivative, the second derivative of the wave function that represents a wave, gives you an idea of the kinetic energy that it entails. It gives you essentially, so if you think in terms of a wave function as a sort of an object, it's not a physical object, it's not an observable, but if you square it, it gives you the probability density, electronic density, which is an observable. So it's related to that. So if you take the second derivative of that, that's what this grad square it gives you an idea of the structure of the kind of internal structure, not just the derivative, the second derivative. Remember, the second derivative can tell you exactly about whether it's what kind of curvature you have. If you look a little bit into the geometry, second derivative tells you about the curvature. That curvature tells you about the kind of kinetic energy that it entails. That's the sort of the quantum mechanical description of kinetic energy, where time is not involved. We do time evolution separately. Okay, let's all agree that this is kinetic energy. Then, if electrons are moving, electrons have a wave function. You can say the nuclei are also moving. Great. We can put the kinetic energy of nuclei to be 0 because we say that they are moving very slowly. So we remove that part. That's the Born-Oppenheimer approximation. We remove that. Then you have this part. So A, when I say A, it's the nucleus. When I say I, it's the electron. So it's a distance. RIA means the distance between the nucleus and the electron. This is also simple. This is a Coulomb interaction. It says that if you take two like opposite charges, they will attract each other. That's why there is a minus sign. Okay. I will not come to this term now. I'll go to this term. This term says this is the distance between two nucleus. Two nucleus will repel each other. That's the distance, no problem. Then we say that, you know what? These electrons, they move very fast. They are very light and the nucleus are heavy, which means the kinetic energy of nucleus is 0. And this term we can treat as sort of a constant, that because you can imagine that that when the electrons are moving around, or it's essentially the probability density of electrons are changing in any way, or the electrons have some kind of this probability densities keep shifting in space. These nucleus don't move so much. So the RAA is kind of fixed. So every time we change or we propagate over the electrons in some way, if we change the density of the electrons, or if there is some kind of change, this will it will adopt. It will be slowly, so we can add it out as a separate term. That means we can say that the wave function that we are dealing with, why did it come up? Yeah, the wave function that they are dealing with is a function of electronic coordinates and nuclear coordinates. That's what we can say. But when we make this approximation, when we say that the proton is much more heavier, motion of electrons does not affect the nuclei because they are too slow, then we change then we essentially come up with an electronic part where we are ignoring something that is purely nuclear part. So for example, this becomes 0. This is a constant term. So these two parts we remove and we are left with this problem. This is an important problem to solve. Rest we can manage. The rest we can deal with some approximations. That will be a good approximation. That changes the Schrodinger equation as well. This is mainly the electronic part that we solve. And important part is now the wave function that you have. Now the wave function that you have, it is still dependent on electronic coordinates, x1, x2, xn, but it becomes a parameter of the nuclear coordinates, which means you fix the nuclear coordinates, then you can have a certain electronic distribution, and you can vary it slowly in the potential that the nuclei experiences, and that changes the electronic density or vice versa. And this is important because this then helps you, because you have decoupled the motion of electrons and nuclei. This helps you to do the geometry optimization because you can simply move the nuclear centers and then see how the electronic density rearranges, look at the changes in energy, because everything, all the Hamiltonian part is essentially electronic. That is most important. And then you can have a geometry optimization just like you did for the force field. So that's nice and good. We have also reduced certain dimensionality of the wave function. So far, any questions? Is it getting too confusing, or you're saying what the hell is this? So much text and so many equations. No, I'm glad that it's clear. But if it does not remain clear, if there's anything that you want to ask, do not hesitate. If you're writing in the chat, I'm unable to see it right now. Maybe I'll take a quick look. No, but please just raise your hand and ask a question if you have one. I'll wait for 5 seconds. Okay, let's move on then. So now we have made some simplifications. We know that it's essentially nuclear part we can deal with, but electronic part is important. Let's go back to our hands-on exercise that we did earlier. So let me open the terminal and show you something. So what we did was we did geometry optimization using our GFN2-xTB calculator, and we had an output file, right? In this output file, you go up, up, up. You will see this term called repulsion energy, right? We talked about this. This is essentially the total repulsion energy that you have in the system. Actually, I might want to also show you a DFT one. Is there an ORCA output here? Yeah. So this is an ORCA calculation that I did. It ran just for a second, small molecule. And here, it gives you a decomposition of what are the different energy types. This is something that I wanted to show you so that you can make a connect of what we are talking about. So here it has the dispersion part, and it also gives you the attractive and repulsive different parts, E6, E8 kind of energy. This is the repulsive part, probably. This is the repulsive part. There are the information on timings. Then there is a lot of decomposition of what the population of all the orbitals look like. And here, this is the nuclear repulsion energy. You can make a connect of this to this part. So essentially, when I did an ORCA calculation, I think it's also on the N2H4 molecule. I just did a simple single point energy calculation to look at what energy it has. This constant repulsion term is mentioned here. Then there is the electronic energy, which I'm showing you here, the E electronic. And then there is the 1 electron energy, which is essentially, when I say 1 electron, it is this energy, it is negative. It's an attractive potential. So it's a negative energy. And then you have the 2 electron energy, which is positive because it's the electron-electron repulsion. And this electron-electron repulsion has given scientists a headaches for years, because this is the one that becomes very difficult to deal with. So I hope you have some sort of idea onto what these equations map onto when you do an actual calculation. I did not run an actual calculation here, but it would just be executing some ORCA commands. But essentially, I can show you a little bit about the input geometry that went into it. So this is the input file. You can see it has nitrogen, hydrogen. It's essentially an N2H4 moiety. And we did in our calculation, it estimates the number of electrons, what is the exchange, what is the correlation term, which I'll come to later on. And it loads, makes a sense of the density and does a DFT calculation on it, which we will also talk about. And it gives you the decomposition of energy in individual terms, which I showed you earlier, that you have the potential energy, you have the kinetic energy, does the virial ratio of the potential versus kinetic, and it has the different terms that are shown here. Any questions at this moment? Not? I'll be moving ahead. So this is what I wanted to show you. We already did the exercise, and we already tried to find out what are the different terms. Now let's dig a little bit deeper in this. This is not going away very easily, and it's actually an interesting thing to think about. See, the key challenge in modeling chemistry using this electronic picture, it really comes from this particular term. It gives a lot of headaches because electrons are interacting with each other. There's a repulsion. So if you have like n number of electrons, or let's say you have 10 electrons, if you change the position of one electron, it affects because it's a long range interaction, it can interact with all other electrons. So there is some sort of correlation that is induced. It becomes a n-body problem, which is difficult to solve. That means the total wave function that you have, it depends on all electron coordinates. If you change one, it affects all other of them. And it lives in a 3n-dimensional space. Why? Because each electron has xyz coordinates, right? If you have n electrons, 3 times n, 3n-dimensional space exists, because if one electron is changed, if one electron is affected, it affects others as well, and you have to solve for all of them. So it's a very high dimensional complex object. It becomes very difficult to solve. And dealing with this Coulomb, the correlation in electrons that is introduced by this Coulomb term, is what scientists have been dealing with for a long time. And there is no exact solution yet for general systems. But there are ways to solve it. So let's dig into a bit of history. I want to do it a bit of a story. I don't know if you'll find it very exciting. I find it very interesting to look at, how and when, like, in what way things have been evolving and what people have been doing. So in 1925, Pauli came and gave the exclusion principle. He says that no two electrons can occupy the same state, which means if you have two parallel electrons, you cannot put them in the same orbital. And mind it, the concept of orbital was not there, but since we know it, you know it, I know it, I'm just using it. So he said that there will be some exchange interaction, which means actually I'll go deeper into exchange interaction later on. But we have read about this Pauli exclusion principle when we're reading about atomic structure, even at school, that electrons, if they want to occupy the same special orbital, they have to be coupled. Otherwise, they stay up, right? And that introduces a correlation, which I'll talk about in the next slide. So 1925, Pauli gave this principle. In 1926, Schrodinger came and solved the hydrogen atom. And that was a big leap because the solution of hydrogen atom, it showed that there are all these orbitals that are, there is like sort of a very detailed electronic structure that exists in the hydrogen atom that are, you use mathematical functions called orbitals to explain them. There are energy levels. Bohr had come. So there was earlier, I think 1905 or something, or even before, there was this whole thing of this black body radiation, and people saw that it's not continuous, the spectra, and Bohr came up with the idea that you put an ad hoc sort of a quantization term. It was not just ad hoc. He was a brilliant man with brilliant scientist, but I'm just trying to simplify things. And then Schrodinger came up with this whole wave mechanics of this wave function based description of quantum mechanics, solved the hydrogen atom and showed that it matches the experimental data. And that was the foundational origin of the modern concept of orbitals. But that was not enough. So this gave the concept of orbitals, but physicists have always had some trouble with this whole thing of orbitals. Because it's very much deeply intertwined in the nature of chemistry and goes a little bit more into the chemical side. And you also have to look at different ways of solving the problem. Then a year later, in 1927-28, Thomas and Fermi, they were working in a lot of statistical physics of different particles interacting in systems. They proposed an orbital-free statistical model. They said that, what, I am going to treat electrons using the density of electrons. And that was really brilliant because when you think of density, it's not a 3n-dimensional object because all the electrons, they compose together to form one object, density. It becomes a 3-dimensional object. That was great. And they actually introduced the concept of using density, and that laid the foundation of density functional theory later on that you will see. So they say that I'll treat electrons using density, and because physicists come up with this brilliant approximation, which sometimes we also known as the spherical cow approximation. If you have not heard about it, look it up. It's a fantastic joke about how things are simplified and yet we derive value out of it. They said, okay, it's a uniform gas, like an ideal gas, but there are interactions and whatever, but it's a uniform gas. There is no structure in it. It works well for solids because if you think of solids, if you think of metals, you essentially have like, a static kernel of or like static base of a material, and then there are these electrons that are that can be described as plane waves moving around, and then they can go into the conduction band, or for metals it's like they can conduct very easily, they move around very easily, so and they are not very tightly bound. So this thing works well for solids. It gave some qualitative descriptions, but it did not include the exchange interaction that Pauli had described. So Dirac, brilliant scientist who also had developed some many fundamental things in quantum mechanics, he added the exchange interaction in the Thomas Fermi model. He said that, you know what, you also need to include the exchange interaction, and that's how the first sort of the precursor of the density functional theory, DFT, it was the Thomas Fermi Dirac TFT. They have no relation in terms of acronyms, but that came up in the 30s based on all of these separate events. Well, they were not separate in the sense that people read each other's paper, talked to each other probably, but in this period, 1925 to 30, there was a lot of rapid development, and we'll focus a bit on what is exchange. So electrons are fermionic particles. That's a sort of ad hoc thing that I'm saying, that we believe, we agree within the scope of this course, they are fermions. They must obey a certain kind of statistics given by the Pauli's exclusion principle. You could say that. It's a little bit more intricate than that. Electrons, if they have the same spin, they cannot be close to each other, which means if they have the same spin, they will be farther away. If they are far away, there will be lower Coulomb interaction, because if you are far away, you will repel each other less. If they are close to each other, there will be more Coulomb repulsion. So this exchange interaction, this is not a force, but it's a statistical description of how electrons, fermionic particles, behave, and it creates a correlation in the electrons just by the very nature, the quantum mechanical nature of the system. It is deeply rooted in relativistic quantum field theory. Feel free to read more about it. I'm not going to touch it in the scope of this course. And what it also says is that if you exchange an into electron, that wave function changes sign, which is, you can show that it's consistent with Pauli's exclusion principle. So this essentially introduces a correlation between electrons, because there is lower Coulomb repulsion when electrons are if electrons have upspin, if they're both upspin, there is lower Coulomb interaction. Continuing our history, you see, they just to revisit, Thomas and Fermi had independently proposed this orbital-free model treating as gas, and Dirac added the exchange interaction. So Dirac said that how do you introduce this exchange interaction between electrons? He said that, okay, you still treat electron as a gas. You say that there is the exchange correlation depends on the local density at that particular point, because it's a uniform gas. We only care about what is the density at that point, and he came up with an analytical expression. It might sound a bit simple. The mathematics of it is not simple. It's simpler than many other formalisms. So if you look at a textbook, you will still be able to grasp it. But the beauty of this approximation is that this actually laid the foundation of how we deal with exchange and correlation even today. And this is still applied to solids in a certain modified form. Dirac's approximation said that the exchange interaction that you have, it's only dependent on the local density of the homogeneous electron gas. Later on, when we talk about exchange correlation functionals, we will see how we slowly build upon this. So what happened between 1925 to 30, especially, this laid the entire foundation of how DFT, or how it essentially revolutionized chemistry. Someone, okay. At this moment, are there any questions? Pallavi.
So this DFT, if we check that exchange rate, is it on time dependent or time dependent? I mean, if we consider the Schrodinger equation, we do time dependent and independent. So in DFT, how we can see that
So
for exchange rate?
indeed, so what everything that I'm describing here, there is no time in it. It's all time independent. If you want to add time to it, what you do is what you can show is that the time part of the Schrodinger equation, you can essentially factor it out and you can do a propagation of the quantum state. So in all of
Okay.
these explanation, there is no time. There is also time dependent DFT formalism, but we will not be getting into it. But in all of this, there is no time. There is also density functional theory based molecular dynamics simulation where you do, sorry,
Mm,
where you do move particles in time, but there
mm,
you make an approximation, you still make the Born-Oppenheimer approximation. You say that, okay, I am now moving the nuclei and propagating a nuclei in time as classical particles. And then you do the entire
mm.
calculation of the energetics and density using using the quantum mechanical formalism. So there also it's not, if you really want to do a truly time dependent thing, you would also have to, you might have to go beyond the Born-Oppenheimer approximation where the nuclei are also, you can no longer sort of ignore the motion of nuclei. But that will be a little bit out of this is indeed a good question and something that wants more thought. But in all of this, no time.
In molecular dynamics, we need to consider that time dependency if we do.
Yes, yes. So in molecular dynamics, you can propagate system in time because you're essentially solving the Newton
Mm,
equations of motion.
yeah.
But what you do
Mm,
then is that you propagate your nucleus using classical
mm,
methods. You essentially are saying that because nuclei is moving slowly, I can move it at a different time scale yeah, and using a classical method, I can simply propagate it in um, using a classical Hamiltonian. And then I do all the calculation of the energies and whatever in the system using the electronic structure theory. So there is a time component involved there, but it's not really the it's not fully quantum mechanical there.
okay.
You still work within the Born-Oppenheimer approximation. Okay. I
Okay.
hope that answers your question. Any other questions? No, then we can move forward. But feel free to ask a question at any point of time. So, you know, Fermi and Dirac came up with their model. Thomas and Fermi came up with their model. Dirac improved it, but it has limitations. It describes solids where the electrons were loosely bound, because there you can say, it behaves like a gas. But whenever you had strongly bound, well-bound electrons, when you have certain kind of electronic structure, it would not describe those systems. And Schrodinger, when he introduced these orbitals, they worked well. They inherently worked well for the electronic structure of the molecules. Within all of these depths, you see there were two parallel tracks going on. Thomas and Fermi, they were taking the statistical track. Dirac improved it in 1930. Along at the same time, in 1928, Hartree came up with the Hartree method, where he assumed that, okay, it's difficult to essentially make calculations on this. Just one moment. He said that, okay, this is difficult to deal with this, this Coulomb interaction or the entire field. So what I'm going to assume is this is simply an average. So I take an electron, I said, okay, rest of the electrons, I forget about them. That's an average field that is moving around. That was also a brilliant approximation. Because you now don't not have to worry at all about individual electrons changing their potential. You say, okay, they are just an average charge cloud. So there is no Coulomb correlation. That you will lose, because in reality the system has Coulomb correlation, but that you will lose because you said you have averaged it out completely. And Hartree also did not consider exchange interaction, just like Thomas and Fermi. So this was later corrected. This was later corrected by Fock. Then Hartree-Fock came in, and they came up with this. So around the same time in 1930s, when Fermi came up with this idea of adding the exchange interaction, Hartree-Fock model was proposed, where you don't have to worry too much about the mathematical detail of it. What it essentially says is that if I have a multi-electron system, multiple orbitals, is there some waiting in the lobby? If I have this system, then then I have to describe it using a determinant. Why? Because if you exchange the rows of a determinant, you get a negative sign, which is consistent with the exchange principle. So that treats the exact exchange within the single determinant formalism. It treats the exchange interaction exactly. Great. Now we have the exchange interaction, but it still does not capture the Coulomb interaction. Why? Because it says that, hey, I take an electron, it experiences the average electric field of all other electrons. Sorry. So there are some drawbacks, serious drawbacks here. Now, before going further, let's just have a simple classical. It's not a quantum mechanical computer density, but just a classical visualization of what I mean by this mean field approximation. What does it look like? So this is just an animation to give you a feeling. Can you see the? So there is actually a charge density cloud here, which does not show up. Okay, it does not show. Essentially, it was supposed to have like a small density cloud that would show you that this target electron, it is essentially experiencing the average field of all of it. But I think it's not. It's visible on my laptop. Oh yeah, it's visible on my laptop, but in the bigger screen, it's like too faint. But please feel free to essentially try this artifact. It will be available and to get like sort of an intuitive feel. But what I want to stress upon is that in the Hartree-Fock approximation, you take an electron, you average out all others and say that it is essentially experiencing the mean field, the average field that of all other electrons, and you don't care actually about the individual one-on-one interactions between the electrons. And that way you simplify your equations a lot, and you are able to solve it. And Hartree-Fock approximation works pretty well, but it has certain disadvantages. It's not accurate enough for many systems, and that's where higher level methods, it could be CASA, say a full CI, MP2, or density function theory comes in. We will not be touching into configuration interaction or MP2 methods in this, but we can, yeah. So now let's do a simple Hartree-Fock calculation using ORCA. How many of you have ORCA locally installed? One person, Anish. Two people. I'm just gonna stop counting. There are some people who have ORCA locally installed. What I would suggest you to do is you can create a simple molecular file using Avogadro or any other software of your choice. It's simple, or you can even grab it. Let me check if I have the coordinates available. That's 3. So what I will do is get 3.xv. This is the, so you essentially have to save it as an XYZ file. So maybe I'll just put it in the chat. Is that okay? So you can either use it from there, or you can construct it by yourself. And what I want to do is I want you to do a Hartree-Fock calculation for that. Let's do one thing. We are doing a lot of theory. Let's do this calculation. So some of you don't have. I understand you don't have this ORCA installed. So I will show you how I am doing it. Okay, NH3 HF demo. Okay, so you can just follow me, and later on I will also show you how to. Oh, sorry, mkdir. So I'm making a new directory, and I'll copy my input file. Here, if you want to use another molecule, you can also do that. So this is, oh my God, this is. Okay. So if you want to create an ORCA input file, it should look like this. You need to provide an exclamation sign HF opt, and then you just have to provide star XYG, charge 0, multiplicity 1, and the name of your molecular file. It might be better to actually put it on the drive as well, right? Is there something in ORCA? No. So maybe I'll go back here, create a new folder, NH3HF, and here I will store the input and the run file. Okay. You will not be able, you are not seeing my screen, but don't worry. I'm just trying to place this folder also on drive so that you can try it on your own, maybe now or maybe later. Okay, so if you go to drive, the Google Drive, maybe I'll share the link again in case you don't have it. Copy link. Yes. Yes, Roshan, I have shared the link. So this is the Google Drive link. If you go here, you will find a folder called nh3_hf. And inside that, I have placed the input file and the XYG file. Okay, so I'll go back to my terminal just to demonstrate what's going on here. What I do is I'll say orca.inp, and we'll redirect it to an out file. It will be very quick. See, and you can see it's doing some of the steps. It's done. Now, if I go to the out file, it has all the references and everything. Now, here it places the input file that I provided it. It said it's a geometry optimization run, right? It also places what is the convergence criteria. This is important because it tells you when the energy will converge and when the overall geometry optimization will be considered to be converged. So it also converts it to internal coordinates, which we have not talked about, but they're also important concepts to understand. And it use they have a brand called Shark now that deals with the integrals that you have. So integrals, when I mean it, essentially is the Coulomb interaction, for example, between the electrons. And it also does some certain fittings if they're available. It generates the grid. So the ab initio method is Hartree-Fock. It uses Gaussian type orbitals, which I'll talk a little bit later about what basis sets are, because I didn't talk about it. You can in fact also provide a basis set. It is using some default kind of basis set here, but you can also provide a basis set to it, which I'll talk about, so you don't have to worry a lot about it. So it is loading the densities, calculating all the cutoffs and everything for this molecule. It makes an initial guess of the density or of the wave function, and then it starts to calculate the energy. So it keeps on calculating until convergence is reached, right? See here, you have the nuclear repulsion, you have the electronic energy, 1 electron energy, 2 electron energy. These quantities are calculated. And then it also computes the charge, that if you were to consider that if you were to look at the electronic density and see what is the effective additional charge on the atomic moiety within the molecule with respect to its neutral state, then nitrogen is slightly negatively charged. It's an ammonia molecule which is considered, and then this is all positively charged. If you sum up all the charges, you will get 0. And then it does some more population analysis, save preparation, final single, and then it keeps on doing. See, here it's a geometry relaxation step. So now it's trying to relax the geometry, move it like, the sort of animation that we saw, that it tries to compute the gradient and then tries to move along so that it reaches finally it will reach the minima. And here is an important point, that it also does a approximate Hessian calculation, means it also approximates the second derivative to understand what kind of surface it has. It keeps on moving along that. Say geometry is not converged because you see it has convergence parameters. Looks at the tolerance, nah, not converged, no. Then it said, okay, let's keep moving. It relaxes the geometry again, does the second cycle, and then it's so on, it goes on and on. I think it will do few more cycles. And finally, it will converge. So it took the whole second took 2 seconds and 297 milliseconds. So very accurate in terms of timing. But if you were using a bigger molecule, that wouldn't be the case. And see here, it says it is making the Fock matrix. The Hartree-Fock matrix that the matrix that we talked about, it's diagonalizing that, it calculates the Coulomb and exchange interaction. Here it is the information is about timing, how much each step took, about essentially evaluating these different parts in the energy, and finally it gets you the single point energy. And if you look at the breakdown that we saw also earlier for a previous calculation, it has a nuclear repulsion, electronic repulsion, 1 electron energy, 2 electron energy, and somewhere it will also give you the exchange correlation energy, that the overall that it has. I think it factored everything in together. So this is something to give you like a feel of what underlies calculation, what is the underlying thing about your Hartree-Fock calculation. It also gives you some rotational constant of the spectra, and it gives you certain citations of the run. You can also visualize the geometry. So you can say is GUI ORCA underscore res.xyz. This gives you the trajectory. And, I'm not using Avogadro to visualize it. I'm using ACE. So yeah, it's not a huge change. There is some change, but not a very huge change. And you can also try to compute try to essentially calculate the dihedrals, 35.7 degrees. You can also calculate the angle that corresponds to roughly a tetrahedral one. Maybe it would be a slightly different one in DFT, but yeah, not a huge difference. It does pretty okay. Were some of you able to run this calculation on your own as well? Did you run into any kinds of errors? Yeah, it worked.
Yes, sir.
So
Are you still?
please,
Yeah.
can you please walk us through the process again of uploading the file and running it through?
Yeah, sure. So are you able to access the Google Drive?
Yes, sir. I've downloaded the file and I've tried to run it through Bash,
Mm-hmm.
and it said permission denied.
Oh, that's a bit weird. Wait. So which command did you execute?
It was ORCA, then orca.inp, the file name.
Can you write this? Can you just execute this command? Which orca?
Um, which one? I don't see it. Okay, this one.
Yeah. Let
Okay,
me
I'll
clear my
try.
screen. So because there might be issues with permissions, that is possible. Are you on a Mac or a Windows laptop?
Windows.
Okay. Windows, it can be a little bit challenging because it's not very trivial very often to set up the environment variables and everything. But I have a solution for all of you. Once we finish this part about density functional theory, I will go to more hands-on where you can do more ORCA calculations. So yeah,
It's the same problem. I try to see if it's a system issue because I think it cannot locate the output directory.
I
To
see. Okay, I think that is a little bit of a custom machine problem. It will be difficult to sort of diagnose the issue on a call here. But what I will do is I will I've shared the Google Colab. I'll share it again in the chat. That's not a problem. And then there you will be able to execute ORCA. So yeah, I think that should work well for small examples. And yeah, try to look into maybe also look into ORCA forum, because I'm sure people have run into these issues, but they are also very specific to what kind of permissions you have on your laptop. And yeah, I think that pretty much boils down to it. You can also download a patched version of Avogadro If you go to ORCA, they will suggest like there is a particular version of Avogadro that you can use that is built for ORCA. So they actually modified that version, and through that you will have a graphical user interface with which you can simply submit an ORCA job using Avogadro. It's I
Okay,
think
sir.
it's mainly for Windows.
I'll try to work through this problem. If I don't, then I'll ask for you.
Yeah, sure.
Okay.
Okay.
Thank you so much.
Yeah, no worries. Thanks. So let's move ahead. So we looked into the components of total energy. We did a simple calculation. And again, to remind you, it does not consider the Coulomb. It does consider the Coulomb's repulsion. This is actually not very correctly written. It actually does not consider the Coulomb correlation actually exactly, because it takes a mean field, essentially takes a mean field approach and makes an average of everything that you have here. So moving ahead, in 1964, so from 1930 to 1964, came a groundbreaking theorem that revolutionized chemistry. It was not just the theorem, but also the work later that so Hohenberg and Kohn had these two theorems about density. And then Kohn-Sam came up with a brilliant way to solve chemistry using density functional theory. I'm not going to put the exact statement of the theorem because that might not be very helpful for you. What you need to know is, if you know the ground state density of electrons, then you know everything about the system in a way. You know the Hamiltonian. That might sound counterintuitive, but the external potential that is felt by the electrons, by external potential, it means that the electron-electron interaction that is there, but also the interaction from the nucleus, that is fully determined by the true density. If you know it, you can determine the external potential, which means you can determine the entire Hamiltonian. This is very powerful. If you want to look into it, you can look into the derivation. There have been, and the derivation is not extremely mathematics heavy, but also a little bit sort of proof by contradiction. For example, for one of these theorems, and then there is the representability problem that we discussed. So please feel free to do some more reading on it. But overall, what you need to know is that this Hohenberg-Kohn theorem elevated the electronic density as the most important quantity of interest. It says that the true ground state density will minimize the ground state energy. These are very powerful theorems. In a way that we have actually solved chemistry. If you know the electronic density, then you are done. The only thing is that it doesn't tell you how you are going to get this electronic density. And that's where the Kohn-Sam's brilliance now comes. So try to get an intuition about Kohn-Sam's thing. So Kohn-Sam came up with a very clever way to solve the Schrodinger's equation. They say that the interaction between electrons is giving us all the headache. If we do mean field, we are still not able to solve it very accurately. Hartree-Fock is not that accurate. So they said, okay, let's forget about the interaction altogether. I'm not going to even average. I like it's non-interacting. That's like, like they must have been really bothered by it. So let's forget about the interaction. Now the orbitals correspond to non-interacting electrons. Orbitals also they correspond to electrons that are not interacting. This interaction part that you are missing, you can shift it. That was missed in the interacting system. Let me move this a bit. You move this into an effective potential. Why I am talking about effective potential is Kohn-Sam said that instead of using a density that maps to external potential felt by the electron, which constitutes the potential that a nuclei electron repulsion, you tune the external potential such that it gives you the correct density, because there is a mapping, right? If you know the true ground state density, you know what the external potential is, which by external potential, I mean where the nuclei and other electrons are, what kind of potential it's giving, you know it. There is some up to a degree of constant, but you know it. There are 4 people, oh no, 40, okay. The other way is also true. If you tune the external potential, then you can get the electronic density. So what you say is that I'm going to work with a non-interacting system, which has the same density as the interacting system. This might, I'll let it sink a little bit. I don't suppose that you will be able to grasp all of it in one go, but keep exposing yourself to it and eventually you will understand how brilliant their approach was and how it really bypassed a very important challenge and helped us solve chemistry. So in the real interacting system, what do the electrons feel? There is the kinetic energy term, that stage. Then, and the kinetic energy term is also affected by the correlation between the electrons, right? If the electrons are like very close together, they will move very fast in a way, or there will be high curvature of the wave function. So there will be high potential energy. Then there is the external potential that it feels from the nuclei, the attraction. And then there is the electron-electron repulsion. So these terms are like sort of intertwined in each other in a way. You can write the whole interacting system. Kohn-Sam said that my non-interacting system, electrons will feel a different kind of non-interacting kinetic energy, because now they are not interacting, the kinetic energy will be different. And the rest of the terms, everything is a fictitious potential that will produce me the same rho, same density. This was the main approximation or the main trick that they played, that really, because see, if you can get the correct density, you get the ground state energy. Your orbitals may be wrong. They correspond to non-interacting system, but you don't care so much about orbitals. You do care about them if you want to do a deep dive into the electronic structure. But if you get the ground state energy, you are solving the system, right? So this is what they did. If you dig a little bit further, the way it works is you will first make an initial guess of the electron density, because you don't know what the real electronic density is. So you make a guess of it. Then you build the effective potential. You say that, okay, I have made a guess. I'll start with an initial guess of the electronic of the molecular structure. You'll say, okay, this nucleus is here, this is here. In ammonia, like, nitrogen is here, hydrogen is here, and then slowly the geometry will also change. But for a given geometry, you say this is my external potential. The position of the nucleus will fix the external potential. Then you say that, okay, I am modeling the Coulomb repulsion as a classical term, that there is an electron charge cloud that's there, like, because it's the density, right? The individual electrons are not there anymore. So in classical electrodynamics, you will see, or electrostatic, you will see that there is the there is like the effective potential of a charge cloud. So you put that term in. There is a small problem with that term, but for now we will not consider that. We say that, okay, this is just the overall interaction of a charge cloud, the field due to a charge cloud, Coulomb field. And then you also put the exchange correlation potential, which could be B3 BP86 or some kind of potential that we'll talk about, but you put the exchange correlation potential in. So these this kind of input that you provide. So you provide, like, you make the initial guess of density, you construct these terms. This helps you build the effective potential. Then you solve the single particle Kohn-Sam equation, which is similar to the Hartree-Fock approach. I did not go in details of that, but essentially this is a form of Schrodinger equation that you solve in a self-consistent manner. So you make a guess, you predict the energy, and you keep doing it until the energy no more changes. We say that it has converged. You do that, and this gives you a set of non-interacting orbitals. They are fictitious orbitals. They are not the real ones, but you calculate the density from those orbitals. And you keep doing it until self-consistency has been achieved. And what you say is that this density will correspond to the true density, because I've used the construction, I've used an effective potential that will give me the true density eventually. This is the whole cycle that goes through. You will have to think multiple times about it, and there are more mathematical underpinnings that I have completely skipped, but I want to give you an idea of what we do in density functional theory. So to break it down all, the exchange correlation potential can be written as a difference between the true system's kinetic energy minus the non-interacting kinetic, because this is the part that we are missing, right? We said there is no interaction, but there is interaction. So we take the differences there. And there is the electron-electron repulsion term, which is dependent on the wave function. The individual wave, the wave function, the many-body wave functions, where you are not considering the electron, where you are not considering the whole density as a thing, but you are considering the wave function of electrons, and you subtract it with the charge cloud, the classical Coulomb repulsion of a charge cloud. If you break it down, if you write and you say that this interacting and this Kohn-Sam Hamiltonian are essentially the same because I'm using a correct exchange correlation function, you will arrive at this term by essentially equating them and doing some little bit of algebra here and there. So essentially what you are trying to do is you need to get an exchange correlation functional that will capture all the effects that were missed during the non-interacting approach. The only problem is Kohn-Sam did not give you a recipe as to how you are going to construct the exchange correlation functional. And since Kohn-Sam theorem came out, people they have dedicated their careers towards building the kind of exchange correlation functional that will give you that will essentially give you the ultimate solution. No one has it. There are varying levels of approximations. There are things that are more suitable and accurate for one thing or the other, but no one has the final answer to it. Any questions here? So the recording of this will be available to all of you. You can feel free to listen to it, read it more and more, and you can also do more readings about it. Um, I have written about it in a little bit more detail in my thesis, also trying to simplify there, but you can also read about, for example, how things are handled in the Hartree-Fock, how exchange correlation works in some textbooks by, I think there's one by Li Yang Par. There's also another one by Zabo that you can read. I can send you the name of those references. So it takes time. It's not going to come eventually. But today what I want to leave you with is, so when you hear of exchange correlation function, you should have an intuitive understanding of what people are talking about. So if there are no questions, I can take a pause and wait for your questions, or I can move ahead. Sir, how to get ORCA underscore trjxyg file? Okay, I will show this to you later on, Manisha. Don't worry. No questions? Okay. Arkadeep, shoot. I cannot hear you, Arkadeep. Maybe you can type your question if there's a problem with the audio. Okay, just let me know when you have a question. It's not a problem. Yeah, just raise your hand or just unmute and speak. So we talked about what is exchange correlation. We talked a bit about the Hartree-Fock approach. What Hartree-Fock does, it does not. It essentially becomes a bit like, okay, I'm not going to deal with all of these electrons. I'm going to say it's an average. Kohn-Sam came up with an even elegant way. They say that I'm not even going to consider the interaction, and I'm going to shift the whole interaction into my potential. And then I leave it to people to break their heads about how they're going to formulate this potential. This is how people have been shifting responsibility. But jokes apart, they have done fantastic job at being able to capture some very intricate effects. Now remember Dirac's LDA, the local density approximation that he used for homogeneous gas model. There was also a spin polarized version of it, where you also can consider the spin of the electrons. It gets 90% of the kinetic energy of electrons, but still not good enough for molecules, because in that 10%, all of the chemistry can happen. So to improve upon LDA, now what does LDA say? LDA say that, okay, the exchange interaction depends on the density at that point, electronic density, right? To improve upon the LDA, you say that no, it's not a homogeneous gas. There is also a little bit of structure. How do I get that structure? I'll also take the derivative of the density, and then I will include it in my exchange correlation term. So it assumes a little bit more structure. That's how GGA comes. You hear of BP86, BLEAP kind of methods. They're all GGA methods. And there are lots of parameters also within the GGA that are tweaked to yield, for example, accurate thermochemistry or geometry or other properties. But GGA also has problems. It only knows the local density and how fast there are changes in the gradient. But when you think about orbital structure, when you think about localization of electrons, when you think about strong bond, weak bond, covalent bond, they cannot be handled well by GGA. GGA cannot do that. When you come up with more intricate structures, there is more curvature in the wave function. So you need to consider higher order terms. But instead of thinking, okay, I'll do a second derivative of the density, you can also think in terms of kinetic energy, which is essentially a second derivative of the wave function. It's more closely related to the wave where bonding happens. Then comes the meta-GGA. Meta-GGA takes it one step further. It considers the local density in the homogeneous gas. Then it says, oh, it's not homogeneous alone. It's not. It has some structure. So there is a bit of derivative. So okay, there is some structure, and then it puts the kinetic energy, which is the second derivative of the wave function. This with meta-GGA, you are able to look into strong and weak bonds. You are able to look into spaces with different gradients of the electronic density, and you can describe the bonds more accurately. But both GGA and meta-GGA, you can see how many carriers of how many people must have gone in making this functional just to live up to the promise that Kohn-Sam said that there is an exchange correlation functional that will solve all your problems within this whole approach that we are taking. And there are Nobel Prizes that have been given out on B3LIP. These people, Becky, Lee, Young, and Parr, they got there was a Nobel Prize awarded for that, and many more prizes and careers have been invested in it. So this GGA and meta-GGA suffer from self-interaction. Now, what is this self-interaction error? When you think of density, you don't think of individual particles. You say that I have a gas that has a repulsion of its own. Now there is a problem, because if I'm an electron and I'm part of that whole density gas thing, I'm also experiencing myself in that sense. I'm experiencing the repulsion that is caused by myself, which is unphysical. An electron cannot be repelled by itself, right? So, and you remember this term was also there, this classical Coulomb repulsion term was also subtracted from electron-electron interaction to actually capture this effect in the exchange correlation functional, but it cannot capture it fully. So there is always some self-interaction error. But in Hartree-Fock, this problem is not there. We only consider the interaction of an electron with a mean field of the rest. This problem is not there. So what we do is in the exchange correlation potential, we also take some Hartree-Fock exchange and mix it. And that gives rise to hybrid GGA or hybrid meta-GGA function. One of the most popular ones that you might have heard of is B3LIP. So you see there is a Hartree-Fock exchange mixed in. Then there is the thing from Dirac, the thing that he did in the 30s, still coming. Then there is the GGA part. So you essentially put also the gradient of the electron. Then there is another part with local spin, the Dirac's part, it mixed in a certain way. There's the exchange part, then there's the correlation part. Then there is another correlation part where you take the leap. So there was another sort of term given by in B3LIP. There was this LYP, Lee, Young, and Parr that came up with, and then you also subtract the correlation from the from that was given by Dirac. I won't be able to give you exactly why these terms arise in a certain manner right now, but this is like the overall construct, and there's a lot of physics, but also a lot of parameter fitting that goes into building such kind of functionals, and people have dedicated their careers towards building functionals. This gives you some intuition of what the functionals are. I want to take a moment here and ask you if you have questions here. I would be surprised if you did not have questions here. There is a very interesting question about Arkadeep. How far in depth do we need to know about exchange correlation functional? Is it essential to understand DFT? That's a good question. Let me give you some practical perspective. I was interviewing someone who did a PhD in catalysis, essentially using density functional theory for transition metal complexes. I asked her some question about what is a GGA, meta-GGA, hybrid GGA, hybrid functionals, and she couldn't explain all of it very, very clearly. Yet she did very well in her research. So from an application perspective, if you know what works well for what kind of system, you will be okay. But if your main job is to do accurate simulations, or if you're if you're a computational chemist, you are working with new kinds of systems, it's good to have a thorough level of understanding of what the effects are. I don't expect that you should be able to construct a new function itself, but you should be able to have some understanding. For example, if you ask me construct the whole B3LIP, I have not done it. I think I will have to read a lot about why B3LIP came up with this kind of parameters, but I have a physical feeling of why B3LIP works for certain systems, why other functionals are, why for example, if you go with, if you want to do if there are states where other spin states are also closely located, so there are two states which are closely located, why you need to use a hybrid functional there. And if the states are very close, if you have singlet triplet that are kind of mixed up in the electronic structure, then the entire DFT might not work, and you have to go to, for example, a CASA-CF like approach. So to have this fundamental level of understanding of the underlying physics or chemistry, that is important. Two, for example, you will never have to, I don't say never, it depends on what you're doing, but usually if you're applying, having a sort of average understanding is good. And that's what also worked for me, to see where, like, if I have to do a fast calculation, I need to know what is the level of accuracy that I can estimate, understand from the system, need to have sort of an intuitive feeling about it. The reason I wanted to do all of this thing is that, as you can see, I've still used some equations, but the whole understanding, if you can have an intuitive feeling without having to go to the equations, because if you actually look into the derivation of exchange term in Hartree-Fock, if you go through the step by step, then you will see how certain terms cancel out, and why it's a natural construct in Hartree-Fock and why certain things work better in the DFT construct or in the CASA CI like construct. But it's not necessary to like have that kind of. So take your time with it. You have the materials, you can choose where you want to go in depth. Go in like a lot of depth. I think this is the deepest that will go in this course, and the further material will not be very deep. It will be much more about applying, but you will have a good physical model to think about. So that's a good question, Arkadev. Any other questions? Did people fall asleep or something? No? Okay. Um, who wants to explain or take lead in explaining what an exchange correlation functional is? Anyone? Just give it a try. We just explore, spend some time on it. Let's see what you understood, and have a sort of a discussion so that everybody can benefit from it. Volunteers? Don't be afraid to be wrong. Okay, then I'm gonna volunteer people. Let's see who we have here. Who is at the top of the screen? Doniel, are you here? Would you like to say something about the exchange correlation function? What's your understanding? What do you think the challenges are? Or anyone else? Okay, no problem. Pallavi, please go ahead. Yeah, please go ahead.
Like we visualize that how electrons can avoid each other, and if we with the help of this exchange correlation, we can find it out. And apart from that, this exchange correlation is depend on this Pauli's exclusion principle, as you explained in the starting, and then we carry forward it to correlation effects with some Coulomb's repulsion, and some like with the help of this too, we have seen how the electron density reduction happens, and that it's exactly known as exchange correlation. And I have one more question, is like not related to exact electrons. Like as I have studied the coordination chemistry, in that there are transition we studied like DD transition and charge transfer, all that. In that DD transition, they mention electron transition and hole transition. So by this exchange, can we see the whole transition also? Like how we can explain that?
Yeah. So think of it like this. You can either think of to it just moves in the opposite direction. So if you, I think I'll focus on electrons, but the principle of holes is kind of the same. It's just the opposite side of movement. When you want to think about DD transitions, you could, for example, think of like, if you think of sort of a dimeric kind of a complex which has a highly filled d orbitals or unfilled d orbitals, when they come in close contact with each other, there will be electronic transitions from one d orbital to another, and that is something that will it's not very trivial to study. You need a good level of theory to explain it, and then you can build up the molecular orbitals. So visualize them, and you can see what kind of charge transfer you are looking at. So when you refer to DD transition, it's not really, it could be, but it's not necessarily a time-dependent phenomenon. It's more of what kind of electronic transitions occur. And it could also be that you have very degenerate level of orbitals that are formed by these highly diffuse d orbitals. So when you shine light or some kind of interaction happens, electron can hop from one state to another. So these kind of interactions, and all of these, for this, you need to have a very good description of the exchange correlation function so that electrons are not too smeared out. So for example, if you use GGA, and if you are working with certain molecules or where you have many electrons, d electrons, what will happen is that if you plot the orbitals, the electrons which are supposed to be localized around a certain reactive center, they will actually be spread out a lot. Why? Because there is this self-interaction error, meaning in the whole construct of GGA and meta GGA, the electron is feeling its own repulsion, so it's a little bit more smeared out. And when you put a Hartree-Fock exchange term, so if you put PB0 or B3 you will see that it becomes more and more localized. So when you want to study those kind of effects, or if you want to study, for example, systems where where you have a unpaired electron, and that gives rise to radical-like reactivity, you might want to have a good description of the electronic density at the reactive center. Because if it's not well described, it will be smeared out and you will not be able to model the reactivity. The caveat is that you might also overbind it. So if you have too much of exchange term, you might increase the, so for example, I was earlier working with a ruthenium-oxo complex, a high-valent ruthenium-oxo complex, and there was a radical-like species, ruthenium-oxygen, there were ligands around it. We were trying to see what is a correct description of the sort of the position of the charge density that compared to the radical species, the unpaired electron. If you use B3 then the electron was much more on the, it was on the oxygen, but it was much more towards the oxygen center, a little bit too much. If you did CASA-CF-like calculation, it is so that it is actually a little bit more between the ruthenium and oxygen bond, so not exposed to outside. So it won't be very, very reactive in a radical, or it has to rearrange. And if you do BP86, like a GGA function, it will say it's actually smeared out and it's actually at the middle of the ruthenium and oxygen bond. So these kind of things, if you understand how the exchange correlation works, because what we did is we started to vary the Hartree-Fock exchange part, and we showed that if you, instead of doing like 20%, 15%, if you go to like 30, 40%, you can show that 100% of the electronic density from the unpaired electron almost comes on the oxygen. So these kind of artifacts you can show, and then you can sort of also build more predictive models on it, because someone did some generalized valence band calculations on it to do very fast simulations of the large system that was based on B3LEAP, and we sort of showed that it's not the correct picture, and therefore you are getting wrong kind of reactivity. Unfortunately, we never published that work because I was done with my PhD, but it gave a lot of insight into how different using different kind of exchange correlation function, what kind of effect it has on the localization of the reactive portion of the electronics of the unpaired electron. And I don't expect that you will be able to, that all of you will be able to grasp everything right now. Where did the chat go? But I hope that you are able to get some kind of a feeling, some kind of an instrument to think about it. Roshan has a remark, the exchange correlation function in DFT accounts for quantum mechanical effects. Exactly. Yes, this is the whole purpose of building the exchange correlation function, because Kohn-Sam said that we have a non-interacting system, but we are going to have the density of the actual interacting system. So this whole effect, interaction versus non-interaction, this is all of it is captured in the exchange correlation functional. This is essentially like shifting your responsibility to something else. I'm not going to think more about my wave function and stuff. Let's put it to potential that people will tweak around and do. So indeed, that's true. This is exactly what exchange correlation functional does. Anyone else? Any comments or remarks? I'd love to hear from you. Somehow the chat is not loading very fast on my end. Do you have another question, Pallavi?
I need to read it more about it.
Yeah, I can also send some reading material, and I would say don't get stuck on it. You have understood the idea. Take your time, apply it in different contexts, and slowly you will build the intuition. It's not something that you can build in one day. Or through just one course that you take a theoretical chemistry course and suddenly you are an expert. No, it takes a lot of time. But I think this would be a good start, and these lectures will be available, so you can always refer to it, or feel free to send me an email. Okay. But then we will move ahead to the sort of the last theoretical part. So this is the famous Jacob's ladder, which you will come across. At the bottom of this ladder is the Hartree-Fock method, which is considered less accurate, although it's very important for capturing many important effects. As you go up the ladder, you increase the accuracy, but it also comes with the complexity and computational cost. If you go down, then you are getting more and more simple. So at the bottom, you have Hartree-Fock, then you build with the local density approximation that Dirac came up with. Then you have the GGA. Like I said, it includes also a little bit of more structure into the electronic density. That electronic density is not just a boring sphere. Then comes the meta GGA like MO6L or TPSS, where you also include the derivative of the wave function double derivative. So essentially you include the density, the kinetic energy density that you have. Then you include the Hartree-Fock exchange, which is the B3 MO6PB0 TPSS. So it's hybrid or meta-hybrid GGA. And then you have post-Hartree-Fock methods, which keep increasing you towards the highest chemical accuracy. And it's not necessary that if you use a method like couple cluster, you will get accurate results. You have to think of so many things when you are applying. And that's where, when Arkadeep asked, do we need a deep dive into what level of understanding do we need? The more complex systems you start to deal with, when systems become multi-reference. For example, if you want to understand how the metal complex that sits at the heart of the photosystem 2 in chlorophyll in the leaves work, when you want to understand that and you want to design a catalyst that would do the same but at a much more faster speed of turnover, that's where this kind of understanding becomes very, very important, because then you would know that you cannot deal with the systems using GGA or hybrid functionals. You need a different kind of arrangement. So there, the depth of the kind of depth that you have in electronic structure comes into play. Any questions at this point?
Sir?
Yeah.
The softwares that we are using, so a lot of them are built on these theorems. Is it so? And how do we know which ones to go for, or which one will be best suited for the system that we are working on?
In terms of software?
Yeah. I mean,
yes.
Yeah.
Yeah, go ahead. So please complete your question. So do you mean to say like whether you should use Gaussian or Turbomole or ORCA for your system, or do you mean in terms of the method?
Yeah, isn't it the same thing? Different softwares must be built on different methods, right?
Different software, kind of true, but not exactly. So for example, you can do the same calculation with ORCA, Turbomole, Gaussian, and anything else that does the TFT calculation. There are some differences in the implementation, but they should give you the same result. If you're looking into the kind of approximation that goes into, one of the problems of using software, or one of the challenges with using software, is sometimes there are approximations that are inbuilt that we don't know of or we are not aware of. And then we see, oh, we are getting different results because there is an approximation that we were not aware of. So that is that is important to keep in mind. But then there are also software that are built for different purposes. So in principle, if you do geometry optimization with B3 leap and a certain basis set in ORCA, You should get the same result in Gaussian, you should get the same result in turbomole. But if you want to treat solids, let's say you want to say that I have a nickel 111 surface and I want to do some kind of heterogeneous catalysis on it. There, I think ORCA has some support for these systems, but it's not really built for periodic systems so much. I think that in the newer versions, there is some support, there's growing support. I think Gaussian can handle some surface slabs and stuff, but usually what you will see is that people would use, for example, things like Quantum Espresso or WASP or GPO to handle this system. So these softwares are built for that, or CP2K. But you will see a lot of people use CP2K when they want to do ab initio molecular dynamics simulation, especially with solvent corrections and everything. But people also do gas phase simulations with it. So you really have to choose what tool best suits you best. And like, so for example, you would not use GROMAX if you want to do DFT, because GROMAX is mainly for force field calculations. There, it's molecular dynamic simulations and everything. Is not meant for DFT calculations. Similarly, you don't want to use ORCA or Gaussian for a lot of, although they keep having new features, but they are mainly for this DFT or quantum mechanical calculations. ORCA actually was written originally to do spectroscopic, ab initio spectroscopic calculations, and the software has evolved. My personal suggestion is that get in touch with the ORCA community. They have a very strong, very active forum. If you can also visit them for events, they're very helpful people. I personally went to their, like, they had this ORCA users or day, like sort of a ORCA user meeting. I would go there. I would sit with the people like Frank Nies, Shengfa, and there were many other people there who were experts in their domain, and they would really sit down, look at your output file, help you out. It was fun. I think they have grown to a very large community, so such kind of personal support may become a little bit rare. But I remember when I did first time wanted to do CASA-CF calculations, this was not a core expertise in my group. So I started with some calculation, and my supervisor warned me, this is like black magic. There are many things that go here and there, but I did it anyway. And we both could not make a lot of sense out of it. So we said, let's go together to ORCA user meeting. We went there. We sat down with the experts there. They made us some suggestions. We sat down with Frank Nays. He gave us some time. Very kind person. Helped us a lot. Next year we went again, and later on we published a few papers where we did CASA-CF calculations on some challenging transition metal complexes. So this kind of community, if you build, you will get a lot of support. ORCA people are very, also the manual, if you read, it's like more than 1,000 pages or something, but it's a lot of very useful details that you will not find easily anywhere else. So look into the ORCA manual, make and of course there are other software that you can always use depending on what your group uses. My recommendation is also always to align with things that are free, things that you can install on your laptop and use, because if you have stuff on your laptop, it gives you a lot of freedom to play around. In my time, I had like a 2 GB, I had a Dell laptop with 2 GB of RAM and a bit some processing power. 2009, 2010, I got access to Gaussian software, some other quantum chemistry software, classical molecular dynamics software. And what I would do is I would just keep running some small simulations. It will end. I'll keep restarting, keep running. And that way I learned a lot about many things that I would not have. Built a lot of experience. Every semester I would do something. Okay, this time I ran one iron atom, two iron atom built on clusters, put carbonyl adsorption, look at how bonds are changing. So really playing around with the system. So I would say get what you can do, what you can get access to. Don't get stopped by the barriers. Software and methods, they should give you, yeah, it's a tricky choice sometimes, but don't get stuck there. I hope this long answer clarifies your doubt and perhaps also for other people. If there are no further questions here, then I would like to move further, describing an important concept of basis sets. This is the final theoretical concept, I promise you. Then we'll do some hands-on exercises and we can close for the day. And the next one, what we will do is next time we'll do only hands-on with, like, optimizing bigger systems, using more GFN2-xTB, looking into some more practical calculations. But don't think that these theoretical concepts will go to waste. Trust me, if you get into the field of computational chemistry, if you're doing, even if you're an experimental chemist, some intuitive understanding of these terms will be helpful for you for lifetime, as long as you are in the field. And many people who are even practitioners of it don't have a very good intuitive understanding because of many reasons. Not that they are not good at their work, but just to say that it has proved very useful for me in my work. So a typical method that you solve quantum equations is that you take a basis set. What do you mean by a basis set? Let's do a very simple example. Let's say I want to describe a point in space in my room. I want to say that, okay, this is the point on my wall. How will I describe it? I will take x-axis, y-axis, and z-axis, right? I can also say 1, 0, 0, 0, 1, 0, 0, 0, 1. I can express any coordinate if I take a combination of these things. So this forms the basis of the world around us, the 3D world around us, right? Similarly, if we want to express the mathematical functions of a wave function on orbital, you can use any kind of, many different kind of functions are available. But what you want to do is you want to explain, you want to take such kind of function with which you can create complicated shapes that entail an orbital and something that is computationally easy to operate with. So there are two types of primary functions. So I'm showing this one as orbital, which is written as a Slater function and the Gaussian function. Slater function is a decaying exponential. Gaussian function is essentially a Gaussian, so it's a e of minus alpha r square. Good thing with Gaussian is that they are easier to integrate, and if you take two Gaussians, the product and everything is easier to deal with, computationally less expensive. So what people do is, and STO, the Slater type orbital, they give you the correct kind of decaying behavior. So there is a kind of a compromise. STOs, Slater type orbitals, are more accurate. They give you better, they capture better chemistry, but they are difficult to deal with computationally. So what people do is they take multiple GTOs, make a linear combination such that it gives you the behavior of a Slater type orbital. Using Gaussians to fit different kind of potentials is not a new thing. I actually did it as a part of my master's thesis where I wanted to model the dihedral term and I wanted to make it into a dual basin potential. And there we were like, putting two Gaussian functions together, multiply them and like, contract them in such a way that they would essentially mimic a dual basin potential because polynomials were not the best way to do that. They were not smooth enough very often. So similarly here, what we say that we essentially compact and contract few Gaussian type orbitals to make a Slater type orbital. And that's how we expand. And these basis set, they help us create a good guess of the atomic orbitals. Now, instead of giving you like, all the lectures, let me give you a cool visualization of the basis set of essentially a GTO, a Gaussian type orbital. Can everyone see my screen?
Yes, sir.
Okay, perfect. I hope people have not slept off. So this is a Gaussian type. This is a function of a Gaussian type orbital. It essentially has a prefactor n, and then you have the xyg with raised to a certain power that depends on what kind of angular momentum you have in the space, and then you have the exponential of minus alpha r square, zeta r square, something like that. If you change the kind of angular momentum that you have, then it changes the shape. So what shape is this? Anyone?
Spherical.
This is spherical. It represents s orbital. If I increase a little bit, this becomes like a p orbital. If I add some more angular momentum to it, this becomes like a d orbital. So what I'm doing is I'm changing certain parameters in this Gaussian type orbital. And on a particular atomic center, I am able to generate more complex functions that actually represent what an orbital would look like. And how do we know what orbitals look like? We know it because Schrodinger solved the equation for us that gave us some idea of what the orbitals look like. We have also mapped out the electronic densities that give us an idea that because with orbitals you can calculate the electronic density, mod of psi square, and that gives you an idea of electronic density, and there's some experimental backing to it. So this gives you some. So you can also say, okay, I want a 2py like shape, so it will compute the parameters for you, and this is the 2py shape. Similarly, you can change the visualization threshold. You can decrease or increase the resolution of the grid. That's just for visualization. And you can also change the width. If you make the zeta function a lot higher, it will become more and more compact, more and more localized. If you can also make it more and more diffuse. So that's very much outward shaping. And this can give you these diffuse functions give you things like DD transitions or very exotic kind of bonding behavior. So this I will place in the chat because it's not on my presentation at the moment. Maybe it is, but feel free to play around with it. I also wanted to create something for the molecules so that you have two centers and you keep on adding different kind of function and you would be able to visualize it, but I was not able to complete that. So I couldn't show you anything essentially on that, but I hope I have given you some kind of intuition also for the basis set. What basis sets are, you take some kind of functions and you want to use them to create complex structures that entail what an orbital would be. And then with that, you are able to study chemical bonding because you can like create different kinds of shape, you can capture different kinds of chemistry. Do you have a question? I see a hand raised. No questions? Okay. And I will lower the hand. It doesn't work, but and then we have different kinds of functionals. So what there are triple, you might have heard of this, like there are triple zeta or double zeta functionals. A triple zeta means that there are three basis functions provided per orbital. They're also polarized, what kind of polarization function that you use. And it essentially adds a character of a different orbital to one orbital so that they can bond on each other. And then there are contracted Gaussians with angular momentum that are higher than the valence that are added for polarization that enhances the ability to form bonding in any direction. So these are some kind of, this is again a lot of science, but also a lot of art with building the right kind of orbitals. And this is, I've given a description of some of the popular orbitals. I've also shared a link to my thesis. I've also described some more of them in more details. What you essentially need to know for your system is what kind of orbitals give you good results. You can look into the literature. Many of the transition metal complexes I worked with, I would always do optimization, geometry optimization with the GGA. Always preferably work with a triple zeta def2t VP like basis set. They work very well across the periodic table unless strong correlation effects are involved. Then you need correlation consistent basis set. But this is something that comes with more and more practice. Any questions about basis sets? No? Let's stop for a moment and let's do some interaction. So what's your feeling so far, people? You can feel free to turn on your camera for some time just to chat a bit, and then we can go on to hands-on exercises and close the day later. Anyone? What's your sort of feeling for the session so far? Do you think it has given you something to work with, something to think with? Yeah, and or are you already sort of like phased out, down in energy?
Sir, of course, it was a bit tough. Like, I only understand half of the things. Half of them were bouncers for me. So, yeah, I think it gave me a few more topics to read on, to discover new things.
I understand. See, there are different ways of doing it. One thing is that we could also have jumped directly into the hands-on stuff, but then a lot of it won't be. So for example, people are asking about molecular dynamics and like bioinformatics. So when you want to do any of these, you need to have some kind of underlying basis for understanding where to look. So for example, next time if you want to do a DFT calculation, you know where to look into. If you want to look, okay, I want to understand what kind of correlation function to you. If you want to read a paper, you will be able to look, okay, this is what it means. And you have a sort of a basic understanding. This is also a little bit heavy on content. I understand that, and the next sessions that we will do, it will be very much on like complete hands-on thing. So that we have, that's why I planned a little bit more of time that in the first lecture. I understand it's a little bit too much for you, but if you have gone through this, rest of the thing will feel like a lot of fun. Yeah, so that's the whole that was the whole idea behind it. Anyone else? Most of the people are quite like quiet. Are you still with me?
Yes, sir. As Ayushi said, for a person who is like completely new to it, it was slightly overwhelming. But yeah, it's definitely things to like read upon and yeah, read further.
That's indeed good to know. Anyone else? There are only a couple of people who are participating, and rest are. And I want to motivate you to participate a bit more, so that you can also get the best out of it. Maybe Abhishek, are you here?
So even for me, because I'm actually doing my bachelor's right now. I'm still in my first year, and I thought of picking this up. So it's all very new to me. But I think if I try to understand it, it'll be really beneficial in the long run.
I understand, but who's speaking? I cannot see now.
Akriti Jha. I don't know if it's visible.
Somehow, maybe there's a spotlight. No. Somehow I don't see. I see Akriti Singh. Okay. Somehow when you speak, usually it would come up, but
Yeah,
it's not. It's not really coming up anymore. But anyway. Yeah, I'm glad that some of you have like feel that it has helped, and I promise the recording of the sessions will be available for everyone, because that really helps you to also go back and look into it. I'll try to chunk it into smaller parts, so it becomes a giant video. And let's do some hands-on stuff to before we close out the day. Do you still have energy?
Yes, sir.
Yes, sir.
Okay, let me. So what we are going to do is we'll do some. Oh, sorry. Where did the collab go? Yes, let me close this artifact. Okay. I will put the link to this collab. Copy link. Okay, somehow it's not, the chat is not loading up very fast. Maybe I have to stop recording for now. Okay. So can all of you try to access this collab, and then I'll walk you through, and also using Google Colab, or should we take a short break for 5 minutes?
Hi, sir. This is Satakshi speaking. I had a small question. Sir, actually, I'm from a biotech background, and all of the first half was fine, but after that, for the last 1 hour, I've been phasing out. So I think I'll have to do a lot of self-study, but since I'm going into my master's with biomaterials, I feel that this will, it will help a lot. But since I feel that I'll have to do a lot of self-study, so where can I, ask you the questions when I'm going through the recording and, and again doing my own studies?
You can. There are two prime ways to contact me. You can either join the Slack channel and put a message there, or
Okay,
you
sir.
can send an email. WhatsApp, I would avoid. WhatsApp is only for like very fast messages, and I'm not very responsive on WhatsApp all the time.
Okay, sir.
But we have a WhatsApp group though. Please try to send a message, send an email, and I will be very happy to to help you and guide you around about like and I think if you want to look into biomaterials more and more as the computation power increases, the use of quantum chemical methods becomes more and more important. So that's it's good that you have had this exposure, and I think it will help you in the longer run for sure. Because also if you want to, for example, appreciate or develop force fields for very larger systems, you will need some understanding of the underlying quantum mechanics. And there are already similar. For example, with XTB, you can already simulate molecules that come close to the size of a protein. So that's that already will be helpful. And tomorrow, not tomorrow, the next session that we'll do, I'll focus a lot on XTB. We're dealing with larger systems, slightly larger systems. It will be helpful if you have it installed. If you don't have it installed, I have the collab, and I can also show you, like, if a run takes 1 hour, we will not do it we will not do the demonstration live, but I can show you how to set it up, what kind of things you can do, how you can, for example, look into, if you start with, I'll give you one example. I was working with a 59 atom ruthenium complex. And it took me a lot of time to sample a particular structure that was very counterintuitive. I did a lot of potential surface scans and everything. And finally, I came out, oh, this is the structure that was missing. And I'll talk about it in the last lecture when I do the use case on homogeneous catalysis. And recording start. So we will do all of that. So I did, and then this XTB package came out, and they have this crushed module with which you can look into what different kind of geometries the system will sample. And the first thing that it did was it actually predicted that geometry as one of the low-lying geometries. And I thought it would have saved me a year of time if I knew about these methods. It was simply not there back then, but then these methods are there now. So I'll try to cover as much as possible. If you are not practicing transition metal chemistry a lot on a day-to-day basis, you won't be able to use it immediately, but it will give you things that you can work with. Maybe you can do a short project on it. Good thing is that it runs on a laptop or even in a collab environment, so it's very fast. And the app that I have set up will also be, I will also keep it public and up, but it had a time limit of 5 minutes. So just keep that in mind. Should we take a short break before we do a final hands-on with XTB in collab?
Yes, sir.
Okay. I would suggest, yeah, don't disconnect to the call. I think I'll be back in 5 minutes. And then, yeah, feel free to, walk around a bit, grab a water or a coffee, and then see you in 5 minutes. Hi, everyone. I hope you still have some energy left.
Yes, sir.
Glad to know that. Let's do a little bit of hands-on thing. And what we will do now, we'll set the basis for the next class where we will do only hands-on stuff. So no more theory, but we'll refer back to theory always. Let me share my screen. Let me also start recording the session. The recording is not. Wait. I'm going to leave the meeting and I'll be back again. Hey everyone, can you hear me now? I had some network issues.
Yes, sir.
Okay. So let's start the much awaited hands-on session. I will share the link of this notebook again, just so that you guys are not missing out on the. Okay. So can everyone go to this notebook? You have to make a copy of it. Or actually, if you sign in, it will automatically execute on your own Google Drive. You need a Google account. I hope everyone has one. Let me know if you are experiencing any issue in just getting connected or anything to this notebook. Once you have if you have if you are able to access it, use it. Just you can react it using give me a thumbs up, like I did. Okay, Kavi Bharathi, you're in. Satakshi in. Kiran in. Great. Is there anyone who has not been able to access it? Maybe if you're on a mobile device, I can understand that it might be a little bit challenging to do that. Don't feel obliged to. You can also look at it here and then later follow on. Like, try to do more examples yourself. I'll do a very simple example that gets you some idea of. So first thing is, how many of you have never heard of what a Google Colab is? Do more people. So let me introduce first what Google Colab is. I came across it, I don't know, I think in 2019, 2018 or so. And this is, I think, a game changer in many of my workflows. Why? Because it gives you a sort of a Python environment in which you can do a lot of stuff. It's hosted on Google Cloud. It's a free service. So you can follow along with me if you are already logged in. You can press connect here. You will see that you have the RAM and disk users appearing here. There are lots of other options. If you also have a Google Cloud instance, you can connect to that. You can also connect to hosted runtime, but I wouldn't. And there are sometimes also GPU access that is available on this. I've tried it. It can be useful, especially for some machine learning tasks. Good thing is that it lives completely on the cloud. So if you can connect your Google Drive to it, you can use it like your own computer. And if you're a little bit comfortable with executing some Linux commands, you can also do custom installation. But for today, I don't want you to start getting struck with Linux. What I want you to do, I'll start with. So first, what we do in order to install XTB. Arkadeep, you have a question? Please go ahead.
So the recording is not done.
Oh, the recording is. It is recording actually. Yeah, the recording is going on.
Okay, sir.
Do you see something on your side that it's not getting recorded or something?
Yeah, I got a notification that recording stopped or something.
Yeah, there is a problem actually. If I stop it.